Article 450.10 pertains to fences surrounding areas that house pad-mounted equipment, such as transformers. The requirement is that the fence must be grounded to the transformer ground grid. Now, addressing the specific situation involving a brick wall supported by steel columns surrounding the transformer area, the key factor determining whether the steel columns need to be bonded to the transformer ground grid is the proximity of the brick wall to the transformer. If the brick wall is within 6 feet of the transformer, then the steel columns supporting it must be bonded to the transformer ground grid. This bonding is essential for several reasons, primarily related to safety and electrical fault current management. Firstly, grounding and bonding create a low impedance path for fault currents. In the event of a fault within the transformer or its associated equipment, such as a short circuit or insulation failure, a large fault current will flow. The presence of a properly grounded grid and bonded metallic structures provides a predictable and low resistance path for this fault current to return to the source, typically the utilities transformer or the grounding electrode system. This rapid and controlled flow of fault current is crucial for the proper operation of overcurrent protective devices, such as circuit breakers and fuses. Secondly, when a fault current flows through a low impedance path, it causes a voltage drop along that path. This voltage drop can create a potential difference between different metallic objects in the vicinity of the fault. If metallic objects, such as the steel columns supporting the brick wall, are not properly bonded, they can become energized with respect to ground or other nearby objects. This creates a shock hazard for personnel who may come into contact with these objects. Thirdly, bonding the steel columns to the transformer ground grid ensures that all metallic objects within the specified proximity are at the same electrical potential. This equipotential bonding minimizes the risk of electric shock by preventing potential differences from developing between accessible metallic parts. This is especially important in areas where personnel may be working or where the public has access. Now, let's delve a little deeper into the practical considerations of implementing this bonding. The connection between the steel columns and the transformer ground grid should be made using appropriately sized bonding conductors. The size of these conductors is determined by the size of the transformer and the available fault current. Refer to the National Electrical Code, specifically Article 250, for guidance on selecting the correct conductor size for bonding purposes. These conductors should be securely fastened to both the steel columns and the ground grid using approved methods, such as welding, bolting with listed hardware, or using exothermic welding. The connections must be mechanically strong and electrically sound to ensure long-term reliability. The ground grid itself is a network of interconnected conductors buried in the earth around the transformer. It serves as the primary grounding electrode system for the transformer and provides a low impedance path to ground for fault currents. The design and installation of the ground grid should comply with the requirements of the NEC and should be based on a thorough understanding of soil resistivity and local grounding conditions. Regularly inspect the bonding connections and the ground grid to ensure that they are in good condition and free from corrosion or damage. Over time, environmental factors can degrade the integrity of these connections, compromising their effectiveness. Periodic testing of the ground grid's resistance to earth is also recommended to verify its performance. If the resistance is found to be too high, corrective actions may be necessary, such as adding more ground rods or improving the conductivity of the soil. It's also important to consider the potential for stray currents in the vicinity of the transformer. Stray currents are unwanted electrical currents that flow through the earth and can cause corrosion of buried metallic structures, including the ground grid and the steel columns. To mitigate the risk of stray current corrosion, consider using cathodic protection systems or other mitigation techniques. These systems can help to prevent the flow of stray currents and protect the integrity of the grounding system. In summary, Article 450.10 mandates grounding of fences around pad-mounted transformers for safety reasons. The requirement to bond steel columns supporting a brick wall depends on the wall's proximity, specifically within 6 feet of the transformer. Proper bonding is crucial for fault current management, shock hazard prevention, and maintaining equipotential bonding. The specific steps involved are: firstly, identify the transformer's ground grid. Secondly, determine if any part of the brick wall is within 6 feet of the transformer enclosure. Thirdly, if within 6 feet, use appropriately sized bonding conductors, as per NEC Table 250.102 colon, to connect the steel columns to the transformer ground grid. Fourthly, ensure connections are mechanically sound and electrically conductive, using listed hardware or approved welding methods. Fifthly, inspect and test the connections and ground grid periodically. Now let's talk about some additional considerations for grounding and bonding around pad-mounted transformers. Firstly, consider the type of fence being used. While Article 450.10 specifically addresses fences, the underlying principle of grounding and bonding applies to any metallic structure that could become energized in the event of a fault. If the fence is made of a conductive material, such as chain link or wrought iron, it must be grounded to the transformer ground grid. If the fence is made of a non-conductive material, such as wood or plastic, grounding may not be required, but it's still important to ensure that any metallic components of the fence, such as posts or gates, are properly bonded. Secondly, consider the presence of other utilities in the area. If there are other underground utilities, such as gas lines, water pipes, or communication cables in the vicinity of the transformer, it's important to coordinate with the utility companies to ensure that the grounding and bonding system is compatible with their infrastructure. Stray currents from the transformer could potentially affect these other utilities, so it's important to take steps to mitigate this risk. Thirdly, consider the environmental conditions in the area. If the transformer is located in an area that is subject to corrosive conditions, such as saltwater or industrial pollutants, it's important to use corrosion-resistant materials for the grounding and bonding system. This will help to ensure that the system remains effective over time. Fourthly, document the grounding and bonding system. Keep accurate records of the location of the ground grid, the size and type of bonding conductors, and the results of any testing that is performed. This documentation will be helpful for future maintenance and troubleshooting. Remember that grounding and bonding are essential for electrical safety, and it's important to take these requirements seriously. When in doubt, consult with a qualified electrical engineer or inspector to ensure that the grounding and bonding system is properly designed and installed. Also, consider the application of ground rods. Ground rods serve as additional grounding electrodes and help to reduce the overall resistance of the grounding system. The NEC specifies the number, size, and spacing of ground rods that are required depending on the size of the transformer and the local grounding conditions. Ground rods should be driven into the earth as deeply as possible to reach low-resistance soil. They should be connected to the ground grid using appropriately sized bonding conductors. Additionally, consider the use of exothermic welding. Exothermic welding, also known as CAD welding, is a process that uses a chemical reaction to create a permanent and highly conductive bond between metallic conductors. This method is often used to connect ground rods to the ground grid and to bond steel columns to the ground grid. Exothermic welds are very strong and resistant to corrosion, making them a reliable choice for grounding and bonding applications. Furthermore, consider surge protection. Surge protective devices, SPDs, are designed to protect electrical equipment from transient voltage surges, such as those caused by lightning strikes or switching operations. SPD should be installed at the transformer to protect it from damage caused by surges. The SPD should be properly grounded to the transformer ground grid to ensure that they can effectively divert surge currents to ground.